So, solving a matrix part 2. Okay, so now what do I do with these numbers? We've talked about where the 390 and the 450s came from. These are the lambda maxes for titanium and vanadium respectively. And we also talked about where these initial molar absorptivities came from. So I know the concentration of the standard that I ran. I look at the absorbance that's given by the standard. I calculate for molar absorptivity. I do the same thing for the vanadium. I know the concentration of the standard that I made, and then I know the absorbance that comes from the spec, and then I calculate for the molar absorptivity. So that's where these numbers are coming from. That work has already been done for you. We didn't really see that work go on. They're just giving us these numbers and they go, here you go. We also talked about this mixture, and we said that this mixture, because we're looking at two different components, we have to analyze those at two different wave numbers or wavelengths. So the first one is at titanium's lambda max, and the second one is going to be at vanadium's lambda max. Okay, so now this is where things start to become beautiful in a way, because as long as you are staying consistent with what we're doing, then that's really all that matters. So whichever one, if you notice in the matrices, we have these primes and double primes. Whichever one you choose to be prime and whichever one you choose to be double prime, these equations will work. You just need to be consistent as you start plugging in these numbers, and you'll get the same answer that anybody else will get. Typically, I just choose the prime number as the lowest. So here's A390. I'm going to say that that is representing my prime set. And then at 450, that represents kind of my vanadium numbers, right? So I'm just going to say this represents my double prime set. So now I have basically said, here is my prime, here is my double prime. And now, as long as my numbers stay consistent in this whole setup, then I'll be okay. The same thing's going to happen on what is my X component and what is my Y component. As long as you're consistent, it doesn't really matter. So let's pretend, since titanium's written first here, that this is the X, and then for the vanadium, let's just say that this is my Y. If you didn't set your problem up that way, it doesn't matter. As long as you're staying consistent with what's going on, it's okay. Trust me. All right? Okay, so if I start to look at this matrices now, we're going to start replacing some of these variables and begin to clean up this math problem. The very first one is it says the bracket X. This is the concentration of my X component. Okay, well, I know the concentration, or I don't know the concentration, but I now know what my X is supposed to represent. I've just defined it up here at the top. That X is supposed to represent titanium. So I'm just going to go ahead and write titanium here because I now know that that is supposed to be my X variable. The same thing is going to happen to the Y variable. So if I take a look at Y and I erase it, I have now defined what the Y is supposed to represent, and here I see that my Y is supposed to represent vanadium, so vanadium goes in there. Okay, so now we kind of taken care of what is X and what is Y. Okay, so now look at what happens with this matrix. Here is absorbance prime and absorbance double prime. I now know what those are. I've just defined them right over here. I've said that my prime numbers are at 390, and I've said that my double prime numbers are at 450. So my A prime, because that's the way that I've defined it in my problem, this 390 absorbance is 0.651. So 0.651 goes in there. And my A double prime was 0.547. So 0.547. Okay, so now we're starting to plug numbers into these problems. Now I have to deal with all of these molar absorptivity numbers, right? This is molar absorptivity of Y at prime, molar absorptivity of Y at double prime, molar absorptivity of X at prime, and molar absorptivity of X at double prime. And you're probably scratching your head and you're probably wondering, well, where are all of these numbers going to be coming from? Well, we've already circled two of them. Right here they are. So this is molar absorptivity of titanium at titanium's wavelength, right? Okay, so if I take a look at how we've defined this, we have said that titanium represents my X number, right? So I could actually, if I wanted to, go ahead and write an X there down below instead of titanium. So that could be an X, right? I mean, X represents titanium, and this is the molar absorptivity of titanium, so that's going to be my X variable. The same thing's going to happen over here with this other epsilon that we've not talked about yet. That's titanium, so that's an X number. This vanadium, well, that represents a Y, and this vanadium, that represents a Y. So I can actually go through and just change those over into something that looks a little bit better for my matrix. And that's what I'm just going to do. I'm going to relabel them. Okay, so this is the molar absorptivity of titanium at titanium's 390. Now look, 390 we did a prime with, right? So that's going to be prime. And this is the molar absorptivity of vanadium at vanadium's wavelength. Okay, so vanadium's wavelength is right here. This is a double prime number. So that means that this has to be a double prime. Okay, so there's the first pieces of the information. That's what prime and double prime is going to come in to say. Okay, so what about these other molar absorptivities? Well, we said two components, two unknowns, two lambda maxes. Well, here I've taken my mixture and I've ran it at 390 to get this molar absorptivity, right? This is how we, or titanium standard. So we've taken our titanium standard, we've ran it at 390 to get a molar absorptivity. To calculate this one though, we had to take the titanium standard and run it at vanadium's wavelength. And because we're running it at vanadium's wavelength, this is not a prime anymore. This is representing double prime now because that represents vanadium at 450. All right, so this is titanium ran at titanium's wave number. And this is titanium ran at vanadium's wave number. You have to make the switch that way in order for this matrices to work. The same thing's going to happen down here at the bottom. This number represents the vanadium standard ran at the vanadium wavelength. That's where this molar absorptivity is coming from. But because there's two components, I then have to take the vanadium standard and run it at the titanium wavelength. I have to do both that way. And that's where the 172 is coming from. So because this was ran at titanium's wavelength, well, titanium's wavelength is at 390. That was my prime. That means that this is EY prime. Okay, so that's kind of the concept of what's going on. You take a standard, you run it at its lambda max, and then you take that same standard and you run it on the other component's lambda max. You did the same thing with the chrome and manganese lab. You took chromium, you ran it at chromium wavelength, and then you took chromium and you ran it at manganese wavelength. You did the same thing for the other component. You took manganese and you ran it at manganese wavelength, and then you took manganese and you ran it at chromium's wavelength. So you've got to kind of cross-reference the two solutions. That's basically what we're doing. So now we have all of the data that we need to go in and to start plugging in this information. So if you look at this last column, this is E prime Y and E prime Y. These two numbers are going to be the same here, so I'm just going to delete those and I'm going to plug in those numbers there. Not only that, but if you take a look at this second matrix over here, we can go ahead and start plugging in information there as well. So this is E prime Y at this location too. Okay, so all of my E prime Y's, what number is that? Well, I've just defined it up here at the top. Y represents vanadium. So I need to be looking at the vanadium data. And this is E, which is the molar absorptivity prime, which means that was the one that was ran at the 390 wavelength, right? That's my prime number. So E prime Y is 172. So 172 goes here, 172 goes there, and 172 goes there. All right, in the next component, we see E double prime Y. Okay, so here's E double prime Y, and here's E double prime Y, so those are going to be the same. And then over here in this matrix, here's E double prime Y. So I'm going to plug in that number there as well. It goes in all three spots. Okay, so once I do that, okay, well, what is E? Molar absorptivity. What is double prime? Well, double prime represented vanadium's wavelength. And so that means Y, vanadium, double prime at vanadium's wavelength. So the molar absorptivity of vanadium at vanadium's wavelength, that's 279. So 279 goes here, 279 goes there, and 279 goes there. Okay, now I've got these x's to worry with. I've got this E prime x. So if I look in this matrix here, E prime x is there. So we'll erase it. E prime x in this matrix is here at the top. So it goes there too. And E prime x is here at the bottom as well. So it's going to go in that position too. So E prime x, what is that number? E's molar absorptivity. X represents titanium. So molar absorptivity of titanium, and this was prime, which means at titanium's wavelength. So this is our 678 number, E prime X. So 678 goes here, 678 goes there, and 678 goes there. And then, finally, I get this EX double prime number. So EX double prime, EX double prime, EX double prime. And we now know what that number is. E is a molar absorptivity. X, in this example, represents titanium, and double prime means titanium that was ran at the vanadium's wavelength. Double prime is at 450, right? That's vanadium. So 526 is that magic number. So 526 goes here, 526 goes there, and 526 goes there. So now all of the numbers are listed in the matrices. I just have to figure out how to solve for the matrices, and that's what we'll do in the next